Ladies and gentlemen, it is with great pleasure that I introduce Professor Louise Ryan to you. She is the 2016 Doctor Honoris Causa of the Faculty of Sciences. She hails from Australia, where she is currently Distinguished Professor in the School of Mathematical Sciences at the University of Technology in Sydney. However, she spent 30 years of her career in Harvard, US, where she climbed the ladder all the way from teaching assistant to professor of biostatistics and department chair. I will not go into any details about her CV, but let me just tell you that I count more than 300 peer-reviewed publications and 16 honors and distinctions, which I guess is more than sufficient to convince us all that her CV is very impressive indeed. But not only she is a great scientist, she also developed a great feeling for the injustice that is done in our societies to innocent people. She played a role in the so-called Woburn case about water contamination and the incidence of leukemia in the town Woburn, Massachusetts, due to chemical waste of a company. She was also struck by the elitism of the Harvard Society, and she set up a summer program specifically targeted at minorities, which is still in place today. For that, she earned the Harvard Centennial Medal. Dear colleague, we are all very honored to have you here, and we keenly look forward to your talk on statistics and big data. What is on the blackboard does not concern you. But I guess I understand that we have first a little movie that Ghent University has made in honor of our Doctors Honoris Causa.
De faculteit Wetenschappen verleent haar eredoctoraat 2016 aan Louise Ryan, professor aan de University of Technology in Sydney. Deze dame werd een autoriteit op vlak van het inschatten van risico's op kanker in functie van milieufactoren. Het gaat om een heel moeilijke materie, aangezien de data altijd beperkt zijn en men moet rekening houden met een grote afstand tussen het moment waarop de blootstelling plaatsgrijpt en het moment waarop de kankers optreden of het sterven doorgaat. Haar motivatie om die aardsmoeilijke taak toch aan te gaan, die men vooraf onhaalbaar achtte, heeft ze gekregen naar aanleiding van een incident in Woburn, waar op een lokale plaats plots heel veel leukemiegevallen optraden en een statistische analyse kon helpen om die terug te brengen tot bevuild water door 3 lokale bedrijven.
12 deaths over 15 years, 8 of them children. They think it has something to do with the city's drinking water.
Het was een emotioneel gebeuren dat inspiratie vormde voor een film in Hollywood, Civil Action, met John Travolta in de hoofdrol en ook voor een nieuwe weg in het onderzoek van Louise Ryan. Zij slaagde erin om in de toekomst meer afstandelijke effecten toch ook correct in te schatten, dankzij mathematisch talent, een goed intuïtief inzicht in datastructuren en de bereidheid om in multidisciplinaire context met heel wat collega's te gaan samenwerken. Als we enthousiast zijn om aan Louise Ryan het eredoctoraat te overhandigen, dan is dat niet alleen om haar topprestaties als wetenschapper, maar ook om haar sociaal engagement. Ze slaagde erin om in die toch elitaire universiteit die Harvard was, de drempel te verlagen en een zomerschool te starten voor minderheden. Die bestaat tot op vandaag en ze kreeg er ook van Harvard een prestigieuze award voor. Het is trouwens een gunst en een generositeit die ik ook persoonlijk mocht ervaren toen ik in de jaren 80 al, eigenlijk vers uit Afrika als vrijwilliger, aan een doctoraat begon en door haar daar werd opgevangen en zelfs veel gastvrijheid genoot. Dankzij Louise Ryan hebben we die synergie tussen de theorie en de praktijk van de statistiek terug ontdekt in een periode waarin dat een beetje weg was uit Vlaanderen. Nochtans waren we in Gent bijzonder bevoorrecht geweest, want in de jaren 1830 al was Adolphe Quetelet erin geslaagd om baanbrekend werk op dat vlak te verrichten en kreeg hij daarvoor een van de eerste doctoraten van de Universiteit Gent. Quetelet liet inzien dat aan het Britse front uiteindelijk meer soldaten stierven in ziekenhuizen dan op het slagveld. En zo kon men vele levens later redden. We zijn dan ook bijzonder blij dat de ontmoeting met Louise Ryan de Gentse school van de statistiek terug op het spoor heeft gezet van de integratie van theorie en praktijk. Iets waarmee we met trots terug in de oude traditie van de UGent gaan staan.
Can you hear me? Is that working? Is that working? Is it working now? Good. I think that might be the first time I've had a movie made about you. Very exciting. Thank you very much, Els, for that wonderful. Okay.
Is it loud enough? Can everyone hear?
Can you hear me? I'm not sure it's on. Is it on? Is this thing on? Hello? Hello? Where did it take a moment? I'll try the other one. Try the other one. It's okay. All right. Thank you so much for that delightful introduction. It's a little bit intimidating to have a movie made about you. It was also very touching for me to be reminded of the Woburn case and to be reminded of two of my heroes, the late Steve Lagarkos and Marvin Zellen, who were the real heroes in that case. We used to always joke with, particularly with Marvin Zellen, when we learned that they were going to make a movie about the Woburn case. Marvin used to wonder which Hollywood actor would play him, and we used to have a lot of fun behind his back just talking about which actor would be the one. But I really feel very honoured and privileged to be here today, and I'm particularly grateful to Dean de Jonge and all of the staff from the School of Applied Mathematics, Computer Science and Statistics for selecting me to be get an honorary doctorate from the Faculty of Science at University of Ghent. It's very exciting. I'm actually getting a little bit of deja vu. Last time I was in a Belgian amphitheatre like this, I managed to get my foot tangled up in the seat in front of me. Somebody managed to sit on my foot and I fainted from the pain and had to get carried out by a stretcher in the middle of the presentation. So I always get a chuckle thinking about that. But I have very fond memories of lots of visits to Belgium over the years. But I will now start in with my presentation. So what I'm going to do today is give really some very simple ideas, but just some perspectives on what are the opportunities and the challenges for statisticians in the big data age. Everybody loves to talk about big data these days, and we could spend the evening debating what it is. But I will basically spend a little bit of time giving you a few examples and then talking about some of the opportunities, I think, where we can get involved in some pretty exciting research endeavours. Let me make sure okay, got it. So I think it's no secret as to what we do as applied statisticians. We have a lot of fun using mathematics, probability and statistics to help make sense out of all of the chaos and the data that's floating around all around the world around us, which can sometimes seem overwhelming. But if you have good statistical methods to find the patterns in those data, and you have good applied colleagues to work with you and help interpret those patterns, that can lead you to some great new insights, and that can hopefully improve the world around us. But what's definitely happening is that in these days, in the big data era, things are changing. So what's happening is that and this is my take on what big data means, the data are becoming more complicated. So in many cases, it's not just simple numbers, but it might be images. Some of my colleagues work with analysing text data, which has a lot of challenges just because it's so much more complicated. Data are also collected differently these days, and I'll give you a couple of examples as we move along, where data may be collated from administrative sources. A lot of times the data come electronically, and I'll give you an example where data come from continuous monitor sensors, and often they're coming from very sophisticated sources such as satellite imagery and so on. And finally, there's lots of examples where the data are extracted from social media. So when you've got these kind of sources, the volumes are very much larger than what we're used to, and also it means that the complexity in the volume means that a lot of times our standard statistical methods aren't going to be working anymore. The other trend that's been very interesting in recent years, and this has been something that I've noticed particularly since moving back to Australia, where we may not have the funding to do gigantic studies from scratch and lots of clinical trials, but we have quite good administrative data because we have a nationalised healthcare system and so on. So there's some really amazing opportunities to construct very elaborate databases from linked records. But all of these things mean that in the big data era, we do need to sometimes think differently about how we do our statistical analysis. So I'll give you these couple of examples, and then what I'm going to basically focus on in the talk is telling you about some of the emerging solutions in the big data era. One is around distributed data analysis, and the other is around an emerging field that I actually don't know very much about, but I've gotten interested in lately, and that's called symbolic data analysis. So I think there's lots of opportunities for us to do new things in this era. So in the first example with administrative data, there's a wealth of information around, and I think that these days, because computer systems are so much better and people are just aware of data these days, there's many sources. So for example, you can pull information from hospital records, link that perhaps with mortality data, with census data, you've got ambulance records, and all sorts of other sources of information, for example, health insurance records. A lot of my examples you'll see come from the health arena, but that might be linkable with information such as air pollution levels in the places where people live, social characteristics of the places where people live may be gathered from the census, or all sorts of other surveys that are looking at the world around. So by linking all of these sources of information together, you can suddenly come up with databases that are much richer and more elaborate than you could ever amass just by a single study. I'm not going to have time today to go into all the nuances of what happens with linked data, but suffice it to say that it does give you a capacity to construct elaborate databases that have many different layers of information. One of the very interesting things is that you get what's called a multi-level data set, where the individuals in the study you've got characteristics measured on those individuals, as well as characteristics measured on the places where people live or the hospitals where they're treated and so on. So you get an opportunity to build models that can take into account characteristics at all these different levels of resolution. So that gives rise to lots of interesting statistical problems in correlated data analysis, spatial analysis, and so on. The example that I'm going to go into in just a little bit more detail, it's one that I've worked on now for a few years, but it's turned out to be quite a little bit of a gold mine in terms of giving interesting statistical problems to work on. And it was a fairly simple study in a way, where we're trying to look at the rates of ischemic heart disease gathered from hospital discharge records in New South Wales, Australia. It's one of the states in Australia, the largest state. So we had data on all of the discharges from the hospitals for patients who'd been admitted by the emergency room with a diagnosis of ischemic heart disease, and we had data characterized by the postcode where the patients lived, their age and their gender. We had it over a 5-year period, and we had data on a daily basis. We then had the population data, so you need the population data so that you have your numerator. We had that from the census, and from the census as well, we had a measure of social advantage or disadvantage called the CIFA index, which is the socioeconomic indicators for areas. So it's an index that basically you can think of it as just SES, socioeconomic status, but it reflects education, income, and so on at the area, at the postcode level. So what we wanted to do, it was a bit of a proof of concept where we wanted statistical models that allowed us to link the rates of ischemic heart disease with this postcode level measure of socioeconomic status. We wanted to build like a Poisson model that would allow us to look at covariate effects whilst allowing for spatial correlation as well. But it turned out, oh, and here's a graphical picture that gives you a bit of an indication. So this is New South Wales. The yellow square is the Sydney region. Sydney's quite a densely populated area. Australia, we're all a little bit obsessed with the ocean in Australia, and I think well over 80% of the population lives 100 kilometres from the coast. But what you can see, let's just focus on the Sydney metropolitan area. Here's Sydney Harbour. The dark red here indicates areas where there's high social advantage. So anybody who's lived in Sydney, I know Peter Diggle spent some time in Sydney. This is the posh North Shore part of Sydney, high social advantage. Here's the nasty western suburbs where nobody wants to go, low social advantage. I'm being a little bit facetious, but sorry about that. Over here on the bottom, we have the heart disease rates. And what you can see, again, here's Sydney Harbour, North Shore, low rates of heart disease, western suburbs, high rates of heart disease. So visually you see the association there. So what we wanted to do was a formal statistical analysis that allowed us to correlate the area-specific levels, measures of socioeconomic status, and the rates of heart disease. But we wanted to do it properly, you know, adjusting for age and gender, and looking at time effects, day of the week effects, and so on, and adjusting for spatial correlation. By the way, I'm happy to take any clarification questions as we go along, so just let me know. So there was a computational challenge, though, because when we multiplied out number of postal areas, number of days, age groups, genders, we had 33 million observations. Now, on a fairly ordinary laptop, desktop machine, with this many observations, we couldn't run even an ordinary generalized linear model, or ordinary Poisson model. Everything just choked up. In fact, the problem was that couldn't even get the whole data set into R at the same time. So it was a real problem. So what is this? It's an example where, on the grand scheme of things, you wouldn't call this big data, but yet it was big enough data that it caused me a problem for trying to run the model on my computer. So that could be a definition of big data, something that doesn't run on your computer the way you'd like it to. So what are your solutions? Well, a lot of times the epidemiologists will do things like they'll reduce the dimensionality by doing an age, gender standardization, and that's not a bad thing to do, and it will reduce your dimension quite a lot and simplify your modeling a little bit. But you are throwing away some valuable information by doing that. Another option is get a better computer. And, well, we all work at the university and we all know how hard that is. But it also can be quite expensive. And I also feel that there's a lot that we can do without having to go to get the better computer. I did, for a while, try to get myself onto a high-performance cluster, but that was more difficult than deriving a new method. So I thought it was more time-effective for me to come up with a better method. So I think this last bullet point is really the punchline of what I want to talk about tonight, is that there's a lot that we can do from a statistical perspective to come up with better algorithms. And in fact, a lot of the ideas are fairly simple, and I actually think there's a lot of low-hanging fruit for us to be rethinking algorithms that work better in the big data era. So that's what we did. This work's actually from a few years ago, But it was a very simple idea that worked remarkably well. You've probably all heard of the Gauss-Seidel algorithm from, when you had to take, numerical optimization courses in university. But basically the idea, it's what statisticians often call backfitting. Instead of updating your parameters all at the same time, say via a Newton-Raphson algorithm, you update the parameters one at a time. So you initialize, consider them all fixed except one, update that one, and just keep iterating through the parameters one at a time. So it's a simple idea. In this particular setting, we were able to exploit the fact that if you're only updating one parameter at a time, then you could actually collapse your data. So if I only wanted to update, say, the parameter associated with gender, I could collapse over everything else in my data set. So instead of 33 million observations, I really only needed 2. I needed 2 summary statistics, one for males, one for females. Update the parameter, expand the data out, and then collapse over a different dimension, update that parameter. So by doing this expand, collapse, it meant that each iteration of my algorithm, I had a very small problem that I was solving. So it worked remarkably well, and it allowed us to fit models that were just impossible without having to resort to, say, going to a high-performance cluster. And we could do this all on the local machine. And it worked really well. I'll just take a minute just to show you some of the results. I know that Sir Michael Marmot is going to be getting an honorary doctorate as well. I feel very privileged to be in such august company, but I know that he's done a lot of work in the area of the impact of social factors on health. So this is actually an interesting example. So what we found after we fitted our Poisson model is that when we looked at the effects of age, as people increased in their age, this is just by 5-year age increment, the relative risk associated with ischemic heart disease went up. So you see the rise in the rates of heart disease with increasing age. What you see is that for any given age, males have a higher rate of heart disease than females, but at the older ages, the females catch up to the males. That's a well-known phenomenon. What we also saw was some interesting day of the week effects. So this is with a baseline of Monday. You see that the rates are really low on Saturdays and Sundays, quite high on Monday, and then sort of moderate during the week. And you can have fun thinking of all sorts of hypotheses about why this might be so. But I was recently reading, actually, that there is a bit of a phenomenon that people go out and play lots of sport on the weekend, and so then they end up with their heart attacks on Monday. I don't know if that's true or not. I remember I was living in the States and called up my folks on Friday night, and I said, "Oh, Dad, how are you doing?" He said, "Oh, I've got a bit of a pain in the chest." And I said, "Oh, you better go over to the hospital." And he said, "Oh, no, it's Friday, And then this was happening all weekend. "Oh, no, they're all gone. The doctors don't need to be disturbed on the weekend." It was actually a long weekend, so it wasn't till Tuesday that he went to his doctor, who sent him immediately off to the hospital, and he got put into intensive care. So I thought that was another example of where the rates go up on Monday because people like my dad didn't want to disturb the doctors on the weekend. So, but this is the one that was interesting. If you remember, what we wanted to do was to look at the impact of this variable called CIFA, the socioeconomic variable, on the rates of heart disease. So we fitted 2 models. The first model was the red square model, where we basically just did a Poisson regression where we had the rate of heart disease was a function of age, gender, and the CIFA variable. And what we found was that as CIFA went up, which meant social advantage increased, the rate of heart disease went down. I'll show you another graphic in a minute. But then what we did was we did an interaction effect. We wanted to see whether the impact of CIFA, or this impact of social advantage or disadvantage, changed with gender and age, because there was actually some indication that that might be the case. So I'll show it to you with this histogram here. So just to translate that into more interpretable sentence, what we found that was for a 100-point decrease in the socioeconomic status, there was a 20% increase in ischemic heart disease rates. But when we broke it out by age and gender, what we found that there was quite a dramatic effect. So, for example, let's take the 55 to 60-year-olds. What you can see here is that amongst the males, the rate is about 1.4, so there was a 40% increase in ischemic heart disease rates for a 100-point decrease in CIFA. For females, it was a 60% increase. So what you can see is that the impact of CIFA goes down as people get older, but what you also see is that for any given age, the women seem to be much more susceptible to that socioeconomic gradient than the men. When we first got this result, my postdoc at the time had found a paper that had said that males were the sensitive one. We all knew that wasn't the case, but he'd found this paper where it said that the males were more susceptible to the socioeconomic gradient. So when we got this result, I said, oh, Suba, it must be wrong. Go back and check it. You've got the male-female coding wrong. He went back and checked and double-checked. But in the end, we realized that what we had actually found was an example of Simpson's paradox on the interaction scale. When you take account of age as well as gender, it's the females that are more susceptible. But if you ignore age, it looks like the males are more susceptible because the males get their heart disease at an earlier age than the females. So you get a funny confounding of the interactive effect of age and gender. But that's a little bit of an aside of what the point that I'm trying to make with my talk, which is that we were able to fit quite a complicated model because we had that algorithm that allowed us to fit this model without having to go off to the high-performance cluster. And also because we had it in such a way that you could fit the thing fairly quickly, it meant that you could sit and do some data analysis and explore these kind of effects. Now, it turns out we've been doing some more with these data as time has gone along. So we stepped back and we thought about, well, where do the data come from when you do this kind of analysis? And in fact, the data come from 3 separate sources. So one source is the hospital admissions data. So this is a data set that has 1 row of data per patient, and it tells you how old the patient was, what their gender was, and what postcode they lived in. So that's one data set. There's another data set that tells us in each postcode, in each age and gender group, how many people there were. So that's from the census. Then there's another data set that says for each postcode, what was the level of the CIFA, or the socioeconomic variables. So when we did the analysis before, we had to take these 3 data sources, merge that all together, and turn it into one long format data set that we then fed into, or tried to feed into, GLM and R. So, and by the way, if I was using PowerPoint instead of PDF, this big cross would have come when I clicked next. So you're seeing the cross before. I'm quite ready for you to do it. So the point here is that the old style of analysis, you take your input data sets and you merge those together to create your long format data set, which goes into your standard statistical analysis. So what we started to think about was, do we really have to do this? Is there a way that we can go straight from the 3 separate data sets to the analysis? It seemed a waste of time to have to put it into that single format. So with a PhD student of mine at the moment, we've been looking at algorithms that can try to directly think about where the sources of data come from and how to put them together. So Jared's been working on a hierarchical Poisson model. He's been actually using gamma random effects instead of normal random effects, but the same principle applies if you want to use normal random effects. And what he's found was that when you construct the likelihood and you look at the pieces that you need to calculate, if you look at what you need, the elements that you need in the algorithm, and if you take the data set that comes from the hospital and it's got the list of individuals who have the event, well, all you need there is actually a couple of fairly simple summary statistics. in statistical terms, you need the matrix X transpose 1, which you can interpret as you just need counts of how many males had the disease, how many females had the disease, how many people in each age group had the disease. So you really just need a set of summary statistics. You also need to know in each postcode how many people had the disease. So you don't need that full data set. The algorithm then involves using, there it goes. Using these summary statistics and then iterating and having to recalculate these other summary statistics as you go along. These statistics here are actually sufficient statistics. These are summary statistics because they actually involve the unknown parameters. But it turns out if you sort of dissect the elements of the likelihood that you need to work with, you can actually come up with some nice ways to fit the model and leave the separate data sources where they were to start with. And it turns out that this has got some quite interesting implications for privacy. So a lot of times, if you're trying to work, for example, with a hospital and you want to do an analysis that looks at, say, spatial variation in rates of a particular disease across postal areas, you can spend months trying to go through human subjects review, making sure that you're not getting data that you shouldn't have access to. Can take quite a lot of time and effort to get the permissions to do those kinds of analyses. But it turns out a lot of times hospitals or national data organisations like the Australian Bureau of Statistics, they're quite willing to give you the kind of summary statistics that are in fact all you need to be able to fit quite sophisticated hierarchical models. So there's a lot of potential for recognising that when it comes to fitting some of these models, we actually don't need as much, you don't need the individual data records in order to be able to fit an individual specific analysis. So that's one thing. But more generally, this is an example, a simple example of what you might call distributed data analysis. So I want to go a little bit more broadly at this point and think about distributed data analysis more generally. So you might say, well, why bother with distributed data? Why do I have to think about distributed data analysis? Well, a lot of the times it actually comes that way anyway, so you might as well think about exploiting that instead of, are there ways that you can analyze it in its distributed form instead of having to go to all of that effort to put it back together again? As I mentioned, a lot of times privacy concerns will mean that the distributed data stays that way because people don't want to share the individual level data. Other times, and this is certainly more and more becoming the case, it needs to be distributed because it's too big to fit onto a single computer. So in a couple of minutes we'll start talking about some of the cases that I think really spawned the big data era. So for example, if you're a company that's working with internet data, or you're a Google and you're working with that kind of data, it's distributed and it's definitely too big to work on a single computer. So you need to think about ways to analyze the data, leaving it in its distributed form. And then the other thing is data may well be small enough to fit on your local machine, but still too big to fit into your algorithms. And those of you who have worked with R can probably relate to the possibility of having data sets that no problem fitting on your laptop, but you just can't read them into the R program. So it doesn't take very much effort to think about situations where you really do have to start thinking about how to handle distributed data. So MapReduce was the algorithm that Google invented to handle the analysis of their search data so that they could analyze that data, which was largely just based on logistic regression, but utilizing and keeping it in that distributed form. I always, at this point when I give this talk or variations on it, I'm always curious. So I'd like to just ask if you could raise your hand if you've heard of Hadoop. Wow, that's impressive. So obviously the Belgians are quite advanced. Normally I get a much smaller show of hands. Now, raise your hand if you've heard of Hadoop and if you've got more than just a superficial knowledge and maybe have used Hadoop. That's still impressive. But yeah, so Hadoop is the open source version of MapReduce, and it's basically, and I'll go into it a little bit more detail, it's a way of thinking about computing so that you can, I've heard people describe it as, instead of bringing the data to your algorithms, you send your algorithms out to the data and do your computing out, leaving the data where they are in the first place. There's lots of stuff going on in this space at the moment. Berkeley Spark is a more sophisticated version of Hadoop that a lot of people are becoming quite keen about. But I think it's fair to say that for the most part, the kinds of things that you can do in the Hadoop framework there's lots of great things you can do, but it's still limited, and I think there's lots of opportunities for statisticians to get more involved. But the problem is, and those of you who've used Hadoop recognize that there's a very steep learning curve to start using Hadoop. It's really quite hard. And recently we've been learning about a new technology called Tessera, which is being developed by Bill Cleveland and many of his current and former students in the US. And the way I like to think about Tessera, if you think about what S and R did for object-oriented programming back in the 80s, Tessera is now starting to do this for distributed computing in the 2010s. So it's a very, very exciting development. Can I just ask, has anybody here heard of Tessera? Okay. So we've recently had Ryan Hafen, who's one of the major developers, out in Australia giving us a short course. And it's really quite amazing because it does allow you to think about algorithms that work on distributed data systems, but without having to be, say, a Python programmer or a really sophisticated computer scientist who's able to engage with, say, the Amazon cloud services and those really quite sophisticated systems that support distributed data. So the core analytic model that is used in Tessera and also in the Hadoop framework, it's what's called divide and recombine. So some of the statisticians are starting to talk about divide and recombine. So the idea might be the following. You've got the data out there which are distributed out into a bunch of different subsets. And the data might have already come distributed, or you might get some big mass of data and distribute it. It doesn't really matter. The idea is then that you do an analysis on each of the subsets, and then you combine those analyses into some overall result. And there's lots of variations on it, but a lot of times when you look in the literature and you see divide and recombine, what they actually mean is that, for example, if you're doing a logistic regression, then what you would do, if your data set's too big to read into R and do one logistic regression, you just do your logistic regression in, say, 30 different subsets. You do 30 logistic regressions, and then you just average the results. Now, those of you who can visualize the likelihood that's underlying that, you'll recognize that, in fact, you wouldn't be doing you wouldn't get the exact same answer, but it should be reasonably close. So that's a kind of concept that underlies this kind of stuff. And there's lots of emerging developments, and if you haven't read some of these, I encourage you to do so. Bag of Little Bootstraps is absolutely brilliant approach that's been developed by some of the people at Berkeley. Lots of examples of methodologies that have been using this divide and recombine sort of concept. And there's many, many research questions here that are interesting to ponder and think about. So, for example, if you're going to do a divide and recombine analysis, well, how many subsets should you divide into? What's the trade-off between, having lots and lots of relatively small logistic regressions versus a few larger ones and so on? What is the accuracy of the approximations and so on? So one of the things that I've been thinking about with a couple of my students at the moment is, are there alternatives to thinking about that kind of almost automatic divide and recombine? So for example, instead of just doing your analysis on 20 subsets and averaging those results, are there more clever ways that you can think about doing things? And a great example to think about is just even simple linear regression, where you can think about what are the elements that you need to compute when you do a linear regression. So we can all rattle off the formula for linear regression. It's X transpose X inverse X transpose Y. Well, it turns out if you've got your data spread out into K different subsets, what you can do is to calculate the X transpose X and the X transpose Y pieces in each of those subsets, and then combine those, and you can get the exact answer. So this is an example where you can either do a linear regression in each subset and average the coefficients, or you can think about the model a little bit and say, oh, I can go into each of my subsets, extract out the sufficient statistics, really is what you're doing here, pull out those sufficient statistics, grab those, combine those together, and get the exact answer in the end. So this is a great example where you can use the divide and recombine paradigm, but you can do it in a way that maintains the maximum amount of information, and in fact, in this case, exactly reproduces what you would get if you had the giant computer that would allow you to pull in the full data set and do a standard single analysis on the full data set. So we've been doing a few little explorations on another example using Australian, in this case, Medicare data. So Australia has a nationalised healthcare system, and there is a publicly available data set that provides some simple information on the size of different medical claims and a few different predictors. So what we wanted to do was a simple logistic regression predicting the incidence of what we call large medical claims as a function of age and gender. So it's not a particularly interesting analysis, but we wanted to explore the efficiency of doing these different divide and recombine strategies. And what we were interested in here was comparing the divide and recombine logistic regression, which would be fit separate logistic regressions on each subset and average the results, versus thinking about what are the underlying sufficient statistics and working directly with those. Now, in this particular example, if you think about it, we have age and gender. So in fact, we don't need, hundreds of millions of individual zeros and ones. All we need, we can collapse it down to a table of age by gender and the counts within each age-gender combination. So an alternative analysis here is to reduce the data down to a single contingency table and do logistic regression on the grouped data. So it's analogous to what I was describing a minute ago, where you think about what are the underlying sufficient statistics, compute those in a distributed fashion, and then combine those to get your desired analysis. So what we did was we fitted the same logistic regression, but we did it in 6 different ways. So the first 3 ways are working with the 0-1 data. So just for each individual, as a function of their age and their gender, was it a high claim, yes or no? We did it 3 ways. So one, at least we tried to do it 3 ways, was a standard logistic regression in R. The second one, we did a divide and recombine. The divide and recombine 2 different ways. Tessera, the really nice thing about Tessera is that it allows you to work with a Hadoop cluster if you want to, but it also allows you to just divide your data up on your own laptop. So for example, if you have a data set that's 10 megabytes in size, you can divide it into 10 1 megabyte subsets all stored on your local machine. Tessera is a platform that allows R to pull from those separate subsets in the analysis. So it's a way to do distributed data analysis, but kind of practice it on your own machine instead of having to go to the full-blown Hadoop cluster, which is a bit complicated because you need to be on Amazon Cloud or you need a cluster or something like that. So Tessera, we're able to do 2 different divide and recombines here. The last 3 examples, we worked with the collapsed data. So what we did there was we collapsed down to just a table of age by gender and then high versus low claim. And we did this 3 ways. One, we did it just all on the local machine. Second one, we used Tessera to collapse the data, but still working from the local disk. And then the third one, we had our data out on Hadoop. So here's the plot that we got. And hopefully it shows up fairly well. I'm not sure how visible it is from the back. But it's really quite interesting because what we found was that on the x-axis, we've got the file size. So what we did was we basically created data sets of increasing size by adding extra years of data to our analysis. So the x-axis shows the file size. The y-axis shows the log operation time. The solid lines at the top show the analysis that it's conducted on the 0-1 data, whereas the dotted lines at the bottom show the analysis based on collapsing back to the age by gender and outcome table. And a couple of things that leap out. First of all, the analysis done on the local machine, once the data pushes past a certain size point, it just stops working. You get to a point where you just can't use your local machine anymore. You have to go to some kind of distributed data system. What you also find is that when the data sets are small, using something like Hadoop is a bad idea because there's an overhead involved in using Hadoop because you've got a lot of time spent reading and writing from an external disk. So you lose time using Hadoop. But as the data set increases, it scales, and as data sets get bigger, it takes longer to run, but it runs. And so you see the scaling going on there. But the thing that really leaps out is that if you can find a clever way to collapse the data, instead of analyzing it just as it happens to come along, you can have a really significant saving in your execution time by doing that. So in a way, one of the areas that I've become interested in lately, and I'm unfortunately not going to tell you too much about this topic because it's still new to me, but I'm finding it very interesting. This idea of thinking about what are the summary statistics that I can extract from my data, that I'm looking for summary statistics that ideally will keep all of the information. So ideally you're looking for sufficient statistics. Are you working with an example where there are sufficient statistics that you can gather and do your analysis using those? Or if you can't do that, are there summary statistics that you can grab that maybe will give you most of the information but still allow you to do that in a much more computationally effective way? So the idea of symbolic data analysis is all about looking at ways of generalizing the concept of summaries to think about how can I come up with ways to extract meaningful symbols from my data and use those, analyze those instead of the raw data. So by doing so, I can hopefully find something that will retain most of the information, yet at a fraction of the computational cost. So it's a different way of thinking about your algorithms. How can I effectively summarize my data? I'm running out of time here a little bit. Else, have I got, another 5 minutes or so? Okay. So I think I've got time to just give you a little bit of a flavour of where we're trying to go with this. And I wanted to just quickly give you one more quick example where this is an example involving sensors. And it's a project we've worked on with the Hunter Valley, which is just north of Sydney, which is a gorgeous area full of stunning beaches and beautiful wine country and nasty coal mines. So it's quite a mixture of things. And it's very controversial because a lot of the citizens who live there feel that their environment's being really destroyed by all of these coal mines, and it's always in the news and so on. But we were called in to help analyse some data where they had collected data on the levels of particulate matter in the air associated with the passing of different kinds of trains. And they were particularly interested in whether the coal trains taking the coal backwards and forwards from the port to the mines, whether the coal trains were giving off a lot of extra dust. So we had data collected from this monitor, which collected data every couple of seconds, and it measured the levels of total suspended particles and PM10 and other particulate counts. And it also, the data set included information, The data set included information on wind speed, rain, and at any given point, we knew if there was a train passing. So this graph here, again, apologies if it doesn't show up at the back, but what we show here with the coloured dots is whether or not there are different kinds of trains passing. And you can see that it's quite a messy, challenging data set. There's lots of autocorrelation in there, lots of noise. We started fitting some models, and I won't go into details about it, but suffice it to say, we again ran into trouble where my university issue laptop just wouldn't run the models, and so we had to come up with some ways to try to do things a little bit differently. What we've started to explore is the idea of symbolic data analysis, whereby if instead of trying to analyse the data, the every 6-second data, if you can extract it down or summarise it down to a lower level, aggregated level, hopefully you can retain much of the information, actually removing some of the complexity and keeping a lot of the features of interest. So here's a graphical display that illustrates the concept behind symbolic data analysis. So instead of having those measurements every 6 seconds, what you can think about is within a time frame, so this would be in 10-minute increments, I can construct a histogram that shows, it's a histogram of the total suspended particulate levels in each of those 10-minute increments. And what I can then try to correlate that with is the number of trains that were going past, or the average amount of time that there were trains passing in that interval. So symbolic data analysis would start to think about, how do I build a model on these histograms directly? A simpler version of the symbols might be just calculating a mean for each of those 10-minute intervals. But by computing a histogram for each of those 10-minute intervals, you're actually keeping a lot more of the information in your data set. And hopefully you can do almost as good a job in a much more computationally effective way than working with the raw data. So this is an example of symbolic data analysis. So it's an area that's, I think, fairly new, and I think there's a lot of interesting opportunities for us to think about in that space. So I'll close now with a couple of concluding remarks. So I think it's a no-brainer to realise that the big data era really is changing the way we have to think about data and the way we access data. I think one of the things that is really important for us as statisticians is that we need to be aware of some of these new technologies like Hadoop, like Spark and so on, that people have been using to work with these large distributed databases. And we need to be on top of that and contributing by thinking about more effective ways to have our algorithms working in those contexts. So it really is a great opportunity. I definitely would encourage you, if you haven't already, to look into this tool called Tessera. I think it's very exciting as a way of, in a way, putting the distributed data system tools like Tessera and Spark in the background, so you don't have to worry about that so much, and you can think about what are the algorithms that I'm going to fit, what are the models that I want to fit to my data, instead of having to worry too much about exactly how do I do it. So I think that's an exciting opportunity, and I just think it's important that we embrace these new technologies if we're going to stay relevant in the big data era. And I'll finish up with yet another silly cartoon and hopefully have some interesting questions and discussion. Thank you. I'm not sure.
Yeah, thank you for giving us a taste through some simple illustrations for a broad audience of how statistics not only comes in to have complicated interpretational challenges met, as our students were showing in the causal inference setting, but equally nowadays with the new challenges of having more standard methods fitted to new data, where it becomes impossible at different levels, and especially with streaming data from supermarkets, you name it, they want to be quick to have a ton of data analyzed in real time. So it's quite nice to see that a lot of the historic insights into likelihood theories, sufficient statistics, whatnot, are now helping to actually construct these algorithms that allow to do lots of analysis in real time of big data. And at the same time, save privacy issues, which is a real nice benefit on the side. So I'd love to take some questions if we have them. Yes, Dave.
In terms of handling summary statistics, you focus on examples with age and gender. Yeah. How far can we go in terms of flexible modeling?
Look, I think that's a really interesting question, and I have to admit we haven't got too far with it yet. But I think that I think it's an interesting direction. So yeah, I've taken very simplistic examples, but if you had, for example, a continuous covariate where you can't necessarily, completely categorize it, you could think about, using the concept of coarsening, which I think has been talked about in the statistical literature. So you could think about coarsening your data, collapsing down to that coarsen framework, do your analysis there. But I think it would be really interesting to say, if I do coarsen my data, how much valuable information am I using? How do I adjust for possible biases that creep in due to that coarsening? But I guess I just feel, and having grown up statistically with the whole concept of interactive data analysis, there's major value to being able to run an analysis, see the results, do something slightly different, that kind of interactive kind of way of thinking. If you're working with a Hadoop system, you can't do that. So I think that by being able to think about ways to reduce your dimension, coarsening it in some appropriate way, it allows you that opportunity to do that interactive analysis. When you get to the final model, you may want to go back and redo it on the full uncoarsened data. But I guess I've been thinking about using the concept of coarsening and seeing where that takes us. I think it's a really interesting direction.
I guess we've also learned that when we coarsen in nonlinear systems, that the bias that shows up as a result can be corrected through simple statistics as well in first or second order. So we had another question.
On these estimates. What about the variance estimate on your estimates?
Yes, excellent question. Right now, That's a really, really good question. You can go through the calculations and come up with a formula that relates the variance of the averaged estimate. I think it's something like I think it's the average of the variance of the individual estimates, but it does open up the possibility of building in some additional model assessment. So for example, if you do your DNR estimate and then you see that your subset estimates actually have more variability than you would expect, that's telling you something as well. As far as I can see, nobody's really explored that very much. The technology is just so new. I think that there hasn't been a lot done. That's why I think it's just such an exciting area with a lot of low-hanging fruit. The Tessera package that Ryan Hafen has developed, right now, he actually hasn't even built in the variance estimators yet. So that's something we've been talking to him about, what's the best way to do those variance estimates. Yep. But it brings up that possibility of sort of within and between variability. Yep. But if you can come up with a sufficient statistic solution, then it's just your usual variance. It's just that you're kind of dissecting your likelihood. And so it's your usual variance constructed from, your second derivative matrix. It's just that you're computing it via the sufficient statistics. But you can't always do it that way.
Any questions from non-statisticians?
I was super impressed, by the way, with how many people have heard of Hadoop. Honestly, you're way ahead of the Australians. They're hopeless.
If not, then I have two more things to do at this point. One is to give you a gift from the Faculty of Science. One proposition was a book when I voted against it, so we have this little bear and environmentally friendly high-tech lamp to take on your bike travels. That's one. And secondly, I want to thank the audience for being here, for hearing out a little bit of the new directions that statistics is taken with lots of computational challenges. I would like to invite you to have a drink now, and those of you who have time, and especially, of course, the statistician who came for it, we are very fortunate to have Peter Diggle here, who is the president of the Royal Statistical Society of the UK, one of our most prestigious statistical societies, who are incredibly involved in not just the hard work of the mathematical statistics and the applications, but also in policy and making the world change as a result of doing things based on facts. I think the latest quote from Hans Rosling, whom you may have heard, factfulness, he says that's the stress-reducing habit of only having strong opinions based on facts. A real proponent there of having data-based and fact-based opinions and policies, and I would certainly invite you. He is a professor at Lancaster University and has also adjunct positions at Yale, at Johns Hopkins and Columbia, so traveling the world quite a bit. And as far as the team goes, it's also a lot on environmental statistics and health. So please come back after a drink and a look at the posters, and thank you for being here and sharing this occasion with us. Thank you very much.
Thank you. Thank you very much, Els. I can't resist suggesting that we divide and go and have a drink and then we recombine for Peter's talk later on.